Right, welcome to week 5. Sorry, week 5, but episode 5 of Garden Mechanics. Now, I'm here with special guest Mr. Tramlett. Yeah? And we're here because we're on Salcombe Hill in Sidmouth. And this is one of the more, at the bottom, one of the more ferocious climbs in the southwest. And the reason we're here is because this week's episode is all about incline planes. Now,
That's not why I'm here.
he's here for
Under false
moral
pretenses.
support. Okay, so the challenge question is, Mr. Tramlett wants to cycle up this hill and straight back down to the same place. Now, he wants to average 20 kilometers an hour for the whole journey. Question is, if he cycles up at 15 kilometers per hour, how fast does he need to cycle down to do it in that average speed? All right. You don't have to answer it. He's going to have a go, and we'll come back to it later.
So Salcombe Hill climbs out of Sidmouth with an average gradient of 13%. It's 155 metres long. A similar hill would be Chinaway Hill coming out of Ottery, which has an average gradient of 7.5%. So it's a tough hill. Here is a schematic of the climb. It's a very well-known climb to cyclists for its difficulty and that it's used for hill climb races. We want to average 20 kilometres an hour, so we're going to model it as Mr. Tramlett climbing up at 15 kilometres an hour. However, once you've worked this out, I'd like you to try some different initial speeds. And I want you to see what happens when I use these, what happens to the speed I have to come down the hill. Okay, have a go, and we'll discuss the answers at the end. So this week on Garden Mechanics, we are looking at inclined planes. Now, this is a really important part of your learning of mechanics because so far we've only looked at horizontal planes. Now, horizontal planes are fine. Everything is perpendicular, all the forces act in perpendicular directions, and our life is quite easy. When we start to incline the plane, we suddenly have a problem of angle. Now, the first thing we're going to do is we're going to think about inclined planes and where we might see them. Now, you may well have seen road signs like this, and road signs give the inclination or the slope, the gradient of the road as a percentage. Sometimes they give it as a ratio. It's all a bit confusing, so here's a handy guide for you to understand how gradient works. What does 100% mean, or what does any percent mean as a gradient? Well, 100% gradient means that my gradient is 1. I go up 1 and I go across 1. This means that my angle must be 45 degrees. So 100% gradient is 45 degrees. Now we can work backwards with this. So 50% gradient would be 22.5 degrees. A 10% gradient equates to 4.5 degrees. A 20% gradient would be 9 degrees. So all percentages are a percentage of 45 degrees, not 90 degrees. So the most common ones you'll see will be something around about 10% or 20%, maybe even up to 30%. So if we have a ratio, for example, 1 to 3, this means that for every 3 I go across, I go up 1. So in this way, I have a gradient of 1/3, which I then have to work out using trig. In this case, we've got opposites, so it would be the angle is tan to the -1 of 1/3, which is 18.4 degrees. So when you see a percentage on a sign, remember, it's a percentage of 45 degrees. The coveted crown for the steepest road in the world currently lies with Baldwin Street in New Zealand with a
Heap steep.
gradient of 34.8%.
And it is one
For a short amount of time, a road in Wales held this with 37.5%, but it was taken away from the people of Wales last year. There's been quite a lot of controversy surrounding it.
Oh yeah, nah, not today, Wales. Sorry about that.
Before that, in the UK, the Hard Knot Pass was seen as the steepest road in the UK, in the Lake District. Now, in the Tour de France, a very famous bike race, they categorise the hills by 1, 2, 3, 4 or 5. And this is actually all to do with the gear you'd need to be in to drive up it in a car. So 1 would be first gear, so incredibly steep. And there's also an hors category, which basically means beyond the steepest. And in the Tour de France, the steepest climb they'll go up is about 24% at the Planche de Belleville. It's not just uphill, it's downhill as well. And sports like skiing, downhill mountain biking, all rely on having a steep downward gradient. So the question is, why is cycling uphill so hard? And why is cycling downhill so much easier? It seems like an obvious question, but we need to delve into this. And the answer is all to do with gravity. And to explain how this works, here's a very sunburnt, sweaty man in a garden.
So here is my incline plane. I have a horizontal plane here, which I can raise and incline through degrees up to 90 degrees. Okay, the graduations here go up in 5, starting with 10 and ending at 90. Now the first thing we're going to look at is this situation with no friction at all. Okay, so this plane we're going to model as having a mu value of 0, no friction at all. And what I'm going to do is I'm going to place a particle of mass m kilograms on this plane. And the first thing I want to do is show you what forces are acting when I incline this plane. Okay, so here we have our horizontal plane with our particle on it of mass m kilograms. Now normally at rest on a horizontal plane we only have 2 forces at play. We have a force going straight down, which is the weight of the particle, and we have a normal reaction force back up. Now when I incline the plane, those 2 forces do something really interesting. What you need to pay attention to here is what happens to the direction of the weight. So if I hold my particle here, hopefully you can see that the weight acts straight down vertically. Okay, this seems like an obvious thing, but gravity always acts straight down. Okay, so that component of the force, its weight, will always be straight down. Now as I increase the inclination, you should see that weight straight down stays vertically down. Now I'm just going to hold this in place so it doesn't slide. The weight of the particle is always acting vertically down. If I go all the way up, it's 90, you can see, windy today, you can see that weight acts along the plane because we're at 90 degrees. So in between there, we're going to have some components of force. Now one of the components of force is going to make the particle go down the slope, and one of the components of force is going to push the particle into the slope. So our particle is now inclined at 30 degrees. I'm going to try and hold this still in the wind. But from here, we're going to have one component of force which is going to act parallel to the slope this way, and one that's going to act perpendicular to the slope. And the triangle we're going to draw here is going to be dictated by the angle in there. So we're going to draw this one up and label it up now. So this component here is the one that makes the particle go down the slope. This component here is the one that provides the normal reaction force into the slope. So the bigger this force is here, the faster it's going to go down the slope. It's like 30 degrees out here. Anyway, so we're going to use this as a first example. So this slope is 79 centimeters long. Okay, this particle is m kilograms. I have a 30-degree inclination. My slope is 79 centimeters long. I'm going to place my particle here. So the first thing I'm going to do is we're going to label this diagram. So we have a mass of m kilograms. We have no friction. Our slope is 79 centimeters long. So we're going to label up our forces. The first force we have is our weight downwards. Now our weight downwards is m times g. So we'll label that one on. We've then got a force which is perpendicular to the slope here, and we have one which is parallel to the slope here. This angle in here must be 30 degrees. I'm going to very, very quickly show you why.
Okay, so our angle here is 30, and this angle here on our components of forces must also be 30. This is because if I extend this line down, I have a 90-degree angle here. That makes this angle in here 90 minus 30. So in this case, it is 60. Therefore, because we also have a right angle here, this angle here must be 90 minus, in brackets, 90 minus 30, which equals 30. So we could be more general about it. This angle could be alpha. That would make this angle here 90 minus alpha, which would make this angle in here 90 minus 90 minus alpha, which gives me alpha. Okay, so this angle here is always going to be the same as this angle here, but be really careful. This angle here we never label, just this one here.
So we've worked out these forces. We have mg sine 30 here. We have mg cos 30 here. Now this mg cos 30 is not going to help it accelerate. This force down the slope is the one which is going to cause the acceleration. So we use F equals ma. The force is mg sine 30, and that equals the mass times the acceleration of the particle. So when we divide both sides by m, they cancel out, which shows that m doesn't actually matter. So our acceleration is g sine 30. So when I let go of this particle, it's going to accelerate at g sine 30 meters per second to the minus 2, and it's going to accelerate down the slope and get to this end. So we can work out how long it should take, and now we can work out, we can see if it works. Okay? Let go in 3, 2, 1. That is broken now. Anyway, we can work that out, and hopefully what you've realised as well is because we are frictionless, the mass doesn't matter.
Okay, so the first thing we'll do is we'll draw our particle as a dot, and we'll think about the forces acting on it. So we have a force going down the slope, we have a force going perpendicular to the slope, we have a normal reaction force, and we'll draw on a force this way as well. Now this is the best way to tackle these questions. So the force down the slope is mg sine 30. The force into the slope is mg cos 30. The reaction force, the normal reaction, is mg cos 30. And this force this way would be sort of any resistance force, but there is no friction, so it's 0. Okay, so we're only interested in the force down the plane, so we don't need to worry about these two for this question. So if we start with F equals ma, our force down the slope is mg sine 30, and this equals our mass times acceleration. And at this point you can see that the m's we can cancel. Okay, that m goes and that m goes. Therefore our acceleration is g sine 30, which is 4.9 ms to the minus 2. Okay, so by looking at this, we can see that in a frictionless situation, the m's cancel out. Okay, so let's find the time it takes to descend the ramp. So to do this, I'm going to use the SUVAT S equals ut plus half at squared. Now, our u is 0, so that goes. we end up with s equals a half at squared. I'm going to rearrange this first, so I'm going to write that t equals 2s over a square rooted. Okay, the positive square root is the only one we need. So if we put this in, we have the square root of 2 times 0.79 meters divided by 4.9. This gives me a time of journey of 0.57 seconds, and we'll compare this to our recorded time in a moment. Okay, the velocity at the bottom, we're going to use v squared equals u squared plus 2as for this. The reason we don't use the time for the second equation, for the second calculation, is because there's an error in this already. I've already rounded this number, so we're not going to use it. We're going to go back to an original suvat. So v squared equals 0, u is 0, so u squared is 0. V squared equals 2as, so v squared equals 2 times 4.9. By the way, 4.9 was an exact value, okay, because sine 30 is a half, times by 0.79. We then square root it, and our velocity is 2.8 meters per second. Okay, so we worked out 0.57 seconds. Let's see how this compares to the actual measurement.
2, 1.
So we get a value of 0.63 seconds. So we're out by 600ths of a second, which is quite a good result actually. And it's good that the real life one is slower because in our model we haven't accounted for air resistance. So pretty good calculation, pretty good model. Slightly different because of air resistance.
So in our second example, we have a mass of m and we have a 45-degree slope, or a 100% grade slope. Now, I'm going to say that we don't know the length of this slope, but at the bottom, it arrives at the base of this hill travelling at 10 meters per second. So its velocity is 10 meters per second. The question is, how far is it going to come up the slope before it comes to instantaneous rest? It's then going to come back down. Okay, so we want to work out the distance it's going to go up. Okay, so if we model the particle here, we have a 45-degree slope here. We have the weight of the particle here. One component, another component. This angle here must be 45 degrees. We can work out this component down the slope. That must be mg sine 45, and the component perpendicular to the slope must be mg cos 45. So as the particle moves up, the deceleration is g sine 45.
Okay, so the slope is 45 degrees, so we'll start off with a particle, a point here, and we'll label on the forces. So the force here, going into the plane perpendicular to it, is mg cos 45. Therefore we have mg cos 45 as the normal reaction force. Going up the slope, we have 0 force. Okay, we're not providing any force to this particle up the slope. It's travelling at 10 meters per second, so there's no force, it's at a constant speed to start with. On the way down, it has a resistive force of mg sine 45. Okay, so this is the force in green here coming down the slope. So this is what's going to slow the particle up. And again, we start with F equals ma. The resultant force up the slope is negative mg sine 45, and that equals ma. Again, we cancel the m's because it is a frictionless situation. Therefore, our acceleration is negative g sine 45. It's negative because it is a deceleration. When I work this out, I get a value of 6.93. Should be negative, sorry. Okay, and then we can use a suvat to work this out. So we want to work out how far it travels before it comes to rest. So SUVAT, we know the acceleration, it's minus 6.93. We know that V is going to be 0 because it's going to come to rest. We know that u is 10 meters per second. We're trying to find s, and we don't need t. So we're going to use v squared equals u squared plus 2as. Which one equals 0? Well, v equals 0. We know that this acceleration is negative, so we can change this to 0 equals u squared minus 2as. If we then rearrange this, we're going to have s equals, let's have a think about this. We add this over, u squared divided by 2a. So s is going to equal u squared over 2a. Because we've moved the 2a s over to the left, we've got rid of the negative, which makes sense because s is a distance, so it must be positive. Okay, so s is going to equal 10 squared divided by 2 times 6.93. So we get a distance up the slope of 7.2 meters. Okay, so as I fire this particle up here, it reduces in speed because of this force here. Okay, and that's why it slows down. It will also slow down because of air resistance, but we're saying that that is negligible in this case. Okay, so remember, if you're going up the slope, this green force acts against you. If you're going down the slope, you work with that green force.
Okay, so one last example. I've got my track set up at an inclination of 15 degrees. Place my particle at the top, and I want you to label up and work out the acceleration of the particle down the slope and the speed it's going to reach at the end of this 79 centimeter track.
Okay, so the first thing is to label up our diagram. I've started off the diagram here. So the first thing to do is to label on the weight, which comes down here, and then label on your perpendicular force and your force parallel to the slope. Okay, so this force here is mg. This component of force here must be mg sine 10, and this component here must be mg cos 10. The angle in here, remember, is 10. And if you're still confused about working these out, just go back to basics with your trig ratios. Okay, so that's our diagram labelled up. You can, if you want, put on a normal reaction force off the plane, but you don't need to. Okay, so you could, if you wanted to, put a normal reaction force here. Okay, so we want to know the acceleration. So we start with F equals ma. Our little point diagram, we have a force down the slope of mg sine 10. We have no force going up the slope. We have mg cos 10 this way and the same this way. Now, we're not really using the cos at the moment, but it's a good habit to get into because we will be using it when we have friction. So F equals ma, therefore the force, the resultant force is mg sine 10 down the slope. That equals ma. And I think we're quite used to now realizing that means that a, because I can cancel the m's, equals g sine 10. So our acceleration is 1.7 meters per second to the minus 2. Okay, so to work out the speed at the bottom of the ramp, well, we use our old friend v squared equals u squared plus 2as. We know that our initial speed u is 0, so v squared equals 2 times our acceleration, which is 1.7, times by the length of our ramp, which is 0.79. If we square root that, we get an answer of 1.6 meters per second. So just check you've got the right values for this one. Make sure you've got your diagram labeled up correctly. And then once you've done this, you're ready to move on to task 1.
So the next thing to look at is with friction, and what happens to these planes when we have friction. So quite literally the wheels have come off now, and we are going to look at this without having that no friction condition. So this is far more realistic to the real world. Now, here I have a particle of 5 kilograms, we're modelling it as 5 kilograms, and it is inclined at 25 degrees. Now, a couple things to think about. First thing you'll want to do is label up the components that you know. So we've got our mg this way, which is going to be 5g. We can put this component on, which is going to be 5g sine 25. This component down here is going to be 5g cos 25. Now this component now is important. Previously we didn't use it, we left it out, but now it is important. And the reason it is important is because of the equation for friction. Let's remember the equation for friction. It is Fr equals, good luck doing a mu upside down, Mr. Whitworth. Mu r. Now remember, the mu is our coefficient of friction, and I've made it 0.3. Okay, that's just arbitrary, just made it up. 0.3. Now the r is the reaction force this way on the slope. So this component here of 5g cos 25 is that r value. Now, on my slope, my reaction force will always be perpendicular to the slope. So it doesn't matter how much I incline it, it's always going to stay at that same angle. Okay, come down here, it starts vertically, and it's going to stay at that angle. So, to work out the acceleration of this particle, I'm going to have to factor in this frictional force acting this way. So, I have a frictional force acting this way, which I can work out using mu r. I have a force acting in the other direction, down the slope, which is 5g sine 45. So, I'm going to sort of freeze frame this, and we're going to work through the solution.
Okay, so we're going to start off with a point diagram, and we're going to label on our forces. So the first force, down the plane we have 5g sine 25. Perpendicular into the plane we have 5g cos 25, which for some reason is missing off here. Let's label that back on. Okay, the normal reaction to the plane is Rn here, and we have our frictional force Fr here. Okay, so the acceleration down the plane, we're going to start with F equals ma, and down the plane we have 5g sine 25 minus our frictional force, and that's going to equal 5. Fuck off. 5a. Okay, so let's work out the frictional force. So Fr is going to equal 0.3 multiplied by our normal force, which is 5g cos 25. So we end up with 5g sine 25 subtract 0.3 times by 5g cos 25. This still equals 5a. Okay, well, in numbers, this gives us 20.708 ... Keep as accurate as you can. Subtract 13.32 ... And that equals 5a. So when I combine these and divide by 5, I get an acceleration of 1.48 to 3 significant figures. So by drawing this diagram up here, we're able to work out the forces and resolve them down the slope.
Now, another thing to think about with friction is if I am just left this to slide, it's almost a passive situation. is going to go this way because of this component, and it's going to be resisted by the friction this way. But if I was to push my particle up the slope with a force, then I've got to overcome two things. I've got to overcome the friction here, which is acting in this direction, and I've got to overcome the component force acting this way. So here's your second question. If I push parallel to this horizontal plane, what force do I need to push this way in order to make this particle accelerate at 2 meters per second minus 2?
Okay, so the first thing we're going to do is we're going to take our diagram and we're going to label it up with our components. So we have 5G. We have an angle in here of 25. We have our force down the slope, which must be 5G sine 25. We have our force into the plane, which must be 5G cos 25. Our normal reaction force, because there's nothing else acting perpendicular to the slope, must be the same, so that also must be 5G cos 25. We have our force we're applying this way, and we have a frictional force this way. Okay, so a bit of a complicated diagram. Easier thing to do would be to draw a point diagram. So the force is going this way, 5G cos 25. Force is going this way, the same. It's our reaction normal, and that equals 5G cos 25. Okay, the force up the slope is the F. Okay, and that's what we're trying to find. The forces down the slope are the FR, so the friction, plus 5G sine 25. Okay, so we want to work out the forces going along the slope. So we know that it needs to accelerate at 2 meters per second. So let's write an equation. F, that's our force we're applying, that's F here, minus FR and 5G sine 25, so it's working against both of those forces. That must equal MA. Now in this case, MA is going to be our mass times acceleration, so 5 times by 2. So we have F minus FR minus 5G sine 25. Okay, let's work out what FR is. FR must be mu times our reaction normal. So FR is 0.3 multiplied by 5G cos 25. Okay, so let's put this all together. So we have F minus 0.3 times 5G cos 25 minus 5G sine 25, and this must equal 10. So if I put this all into a calculator and I subtract this number and this number, if I add them over to this side, I can do that straight away actually. So I could do F equals 10 plus 0.3 times 5G cos 25 plus 5G sine 25. And this will give me my force. Okay, so my answer comes out to 44.0, or I'll just put 44.0 newtons. What's really important in this question is you've realised that this force must overcome the gravitational component, 5G sine 25, and the frictional component. Okay, and it must do that in order to accelerate this particle at 2 meters per second.
Cast your mind back to last week's video, I spoke about friction and I inclined a table until objects slid to see which one had the lowest or highest coefficient of friction. Now we can actually find out the coefficient of friction by using this and a particle that we know the mass of. So this particle I've just weighed, and it has a mass of 0.279 kilograms. Now what I'm going to do is I'm going to place it on my plane here, and I'm going to incline this plane until it just moves. And then what I'm going to do is I'm going to mark on here what that angle is. It's going to be fairly accurate, not particularly accurate, but we'll see if, we'll see how we get on. So what I'm looking for is the moment at which it starts to slide, because that means that I'm overcoming the friction. It means that I'm just providing more force with this component than the resistance of this force here. Okay, so I'll come back, so it's around about here, around about 15 degrees. Ooh, I think it's there. Right. Okay, how's that accurate? Okay, so using my brilliantly accurate method, I've decided that it's a little bit above 15, so we'll call it 16 degrees. Okay, so we're going to work out what the coefficient of friction is. For this, I'll hold it here, and yeah, let's do the working.
Okay, so we're going to start this question as we start any other question. We label on our forces, so we have 0.279 G. The angle here is 16. Our force into the plane is 0.279 G cos 16, and the force along the plane is 0.279 G sine 16. We have a, interesting, we have a reaction normal this way, and we have a frictional force Fr in this direction. Now, the first thing to do is draw a point diagram, and the thing is, in this situation, it's actually a static situation. Everything's in equilibrium, okay? The force up equals the force down, the force along the plane equals the force down the plane, so everything's sort of static. We're at the point of moving, but nothing is moving. So we're going to draw a point diagram, and sometimes what I actually like to do is draw a kind of double equal sign like this. So this is our point, and in every direction things are equal. It might look like a hashtag, but trust me, that's not what it is at all. So down into the plane we have 0.279 G cos 16. We have Rn this way. This way we have our friction Fr, and down the plane we have 0.279 G sine 16. Okay, they're all the forces, and we can work out what mu is by setting two of these equal to each other. So what we know is that Rn must equal 0.279 G cos 16, so we can change that straight away. We know that we have no other forces which are going to make the normal force any greater or less. So we know that Fr is going to equal mu times our normal reaction. So Fr is going to equal mu, which we're trying to find, times by 0.279 G cos 16. If we now equate the motion down the plane, so the force down the plane and the force up the plane, we have 0.279 G sine 16, and that must equal the force up the plane. So that must equal our Fr. So that equals mu times 0.279 G cos 16. So actually, it's not too difficult to work out what mu is. To work it out, I need to divide this left-hand side by this bit in brackets. So mu is going to equal 0.279 G sine 16 over 0.279 G cos 16. And one thing you'll notice is, look, this first bit here all cancels. So I end up with mu equals sine 16 over cos 16. And this gives me, I want to work it out, a value of 0.2867, or roughly 0.29, which is interesting because I guessed that it was about 0.3. I'm a genius. Okay, so it's actually quite straightforward in the calculation, but setting it up, you must be aware that these two forces are equal, and that is how we can work out this mu value.
Whenever you get an inclined plane question, do the following things. Draw a line straight down for the weights. Draw two components to make a right angle. Label the angle of inclination here. Label the normal force, and then work out what these components are. That's always the first thing you do, whether it's friction, non-friction, and even if there's a connected particle situation in it. Okay, always work out those components first and then answer your question.
Speaking of answering questions, here's task 2. So we've looked at a lot of the questions we're likely to face with inclined planes, but the good thing about inclined planes is there's a lot of real-world applications. For example, escape ramps with lorries on motorways are often built on inclined planes. Unfortunately, here's quite a sad example of when the calculations weren't particularly good. On Top Gear, they launched a Mini from a ski jump, and actually you can see the maths being used, and it's very similar to what we're doing with inclined planes. So we're just starting with inclined planes. There's a lot more to get into, but have a go at task 3 and have a go at applying these inclined plane situations to maybe some slightly more in-depth questions. Good luck.
That's Salcombe Hill done. Just wait for Mr. Tremblett, and then we'll see what his average speed is and see if we can work this out.
Is that it? An anti-climax at the end.
Yeah?
Too flat.
Okay, so if we say that the distance up the hill is x, and the distance back down is also x, then the whole journey must be x. Okay, so the total journey distance equals 2x. We want the average speed to be 20, so if we write this using speed equals distance over time, we have 20 equals our distance, which is 2x over t. Okay, and what we can do is we can simplify this. We can make this 10 equals x over t. Next thing to do is think a little bit about the graph. Here I have a displacement time graph. Now, our displacement away from 0, which is where we start. Okay, so this is the base of the hill. And we're going to travel up to x. So we're going to go x away from our 0 point, and then we're going to come back down. Now, if I was to do this at the same speed, my graph would look something like this. Okay? And the gradients here, this would be a gradient of 20. Okay? And this would be a gradient of minus 20. Okay, that makes sense? Go up at 20, come back down. So if you go at the same speed, it's quite a simple graph to draw. I'll just get rid of these labels. Now, if I'm to go slightly slower on the way up, here's what happens. So if I go slower on the way up, so my gradient must be less. Say I go about here. My gradient on the way back down must be a lot steeper. Okay, so for example, this might be our 15. This might be our 15 kilometers an hour. And this is the speed we're trying to find, but we know it must be a lot more. Now what I can do is I can think about this even further. So if I go much slower on the way up, I'm going to have to go a lot faster on the way down. Keep going. Now if I get closer and closer here, if I go really slowly on the way up, too slowly, I end up having to travel back down in 0 time. Now this limit here is 10 kilometers an hour. Okay, so if I travel up at 10 kilometers an hour, then it's impossible to get back down in time. Okay, hope you can see this from the graph. Go up at 10, you've got to sort of go, take 0 time, or almost go back in time. Okay, so the further that this goes this way, okay, so that's the slower I go up, but the faster I go down. Okay, let's look at this sort of algebraically. So the time I've got to take, if I rearrange this one, I have 10 equals x over t. So the total time I can take is going to be x over 10. That's my total time. Now, the times it's going to take for each bit are going to be dictated by a very similar equation. So for example, if my speed on the way up is 15, 15 equals x over t, and we'll call this t1. So that's the time it takes to go up. So that, when I rearrange it, time 1 is going to be x over 15. Okay, so the way back down, I might say, okay, I have, let's call it k. I have k equals the same distance x, and it's going to take a different time. Let's call it t2. If I rearrange this, I have t2 equals x over k, k being my unknown speed. Now clearly, t1 plus t2 must equal my total time. And my total time is x over 10. So if I fill in what I know that my t1 is x over 15, my t2 is x over k, and this must equal x over 10. So the calculation I need to do is x over 10 subtract x over 15, and that gives me x over k. In this case, x over 10 minus x over 15 gives me x over 30. Therefore, my unknown speed is 30 kilometers per hour. So in answer to this question up here, if I cycle up at 15, I've got to cycle back down at 30. Now I gave you some more speeds to look at, so let's look at some other speeds. Using exactly the same method, I can find some more pairs. Now, let's have a look. If I go up at 11 kilometers an hour, when I work this through, I have to come back down at 110 kilometers per hour. If I go up at 12, I have to come back down at 60 kilometers per hour. 13, 43.3, and I get a lot more pairs, which I'll fill in now. If I graph this, if I plot a graph of these points, which I've done here, what we find is that if I increase the speed I go up, that's my x-axis. If I increase the speed I go up the hill, I reduce the speed I have to come back down. And actually I can model this using a rearrangement of that formula we just used, and we get 10x over x minus 10. Okay? So the faster you go up, the slower you have to come back down. And this 10 that I mentioned earlier, that line of 10, is actually impossible. And you can see it on this graph as well. If you go up at 10, you've already spent that time going up the hill, so you'd have to travel at an infinite speed to come back down. We've made a good start with incline plane questions. Next week we're going to look at questions with more forces interacting and also what happens when you have connected particles with inclined planes. See you next time.